Thank you. Can you hear me?
Yes.
Okay.
Yeah.
Thanks a lot for the invitation to this nice symposium. Uh, yes, today I'm going to talk about some ideas that we have about the possibility of generating quantum light with free electron lasers. Uh, Let me make clear from the very beginning that quantum light is something very special because it's a state of the light that doesn't have an equivalent in the classical light. This work has been done in collaboration with Fabio Benatti, that is a colleague, a theorist, a quantum optics theorist at the University of Trieste, and Giovanni Perosa, that just finished his PhD in Trieste and is moving to the Uppsala University. So let me start first to try to understand in an easy way what is a laser. Well, a laser, of course, is overall a quantum device. It's a quantum device because it requires a system to be pumped in an excited state, and then the decay from this state that eventually is stimulated by the light, but to have a gain, you need the population inversion. That means that here the state 2 should have a population inversion more state than the state 1. So you have stimulated emission and population inversion. That's not enough to make a laser because you need a quantum cavity, actually a resonant quantum cavity. And it is the fact that you have a resonant quantum cavity that the emission, the stimulated emission, has a phase that is correlated to the position of the stimulated emission. And at this point, you can take some of the electromagnetic generation, electromagnetic energy that is in the cavity out from a mirror that is a partially reflecting mirror. This kind of light has a characteristic, as we will see soon, that can be measured through a photon statistics. Now, what is a free electron laser? Massimo Altarelli already said some basic principle of the free electron laser, but let me recall this principle. To have a free electron laser, you need a linear accelerator, and you need a long undulator. So the electron bunch can undulate and it can generate micro bunches, and these are due to the interaction of the electron bunch with the spontaneous emission of the radiation. And in simple words, what's happening is that as you increase the length of the undulator, the electrons that are faster, they are slowed down, and the electrons that are slower, they are speeded up. And so in the phase space, essentially, you condense the charge in point of the space phase, and these charges are then oscillating in phase, and they are generating what are the spikes, the typical spikes that you can observe in a free electron laser. As already said, this is not a coherent radiation because it's a radiation that is starting from essentially from the background radiation noise. And the reason why this was called laser, I believe, is because of the very, very high brightness of the radiation that you can generate in such a way. But that is, I think, the only characteristic, beside probably the transversal coherence, that a free electron laser has in common with a real laser. Now the point is the following: that if we want to make a laser in the X-rays, you cannot use anymore an optical cavity because, of course, there are no optical cavities that can work in the X-rays. That is the basic issue, and I remember that I started to work on this question when I was a young scientist at the CISA laboratory in Milan with Tito Recchi. At that time, we didn't have any idea how to make, of course, a free electron laser and how overall to make a laser operating in the X-ray domains. But to understand better this question, we need, first of all, to define some basic concepts. So what is classical coherence? Well, when we define the coherence, classical coherence is essentially an ideal property of waves in general, in our case, electromagnetic waves, that enables stationarity in constant in space and time of the property of the electromagnetic wave in our case. That means that essentially, if you look at the longitudinal coherence, that is related to the time that the electromagnetic wave travel without any interruption of the phase. So a monochromatic wave essentially is a sinusoidal wave that has an infinite phase continuity. The transversal coherence instead is something that is related to the size of the surface of the source, and essentially is related to the constant phase in a transversal plane of the propagating wave. So there are two very different concepts here that has to be considered, because longitudinal coherence is more related to the mechanism that is producing the radiation. Instead, transversal coherence is related to the size of the surface. This is the classical statement about coherence. How can we measure the coherence? Well, to measure the first order coherence, what we call the first order coherence, this is defined as a first order correlation between two beams that are overlapping, and eventually is normalized to the intensity of this beam. And this can be measured, for example, through an interferometer. There are many different types of interferometer. Here we are talking about the Young interferometer, which is probably the first interferometer, where the light that is emitted by source is passing through two holes here, and you can see the interference on this screen that is set at a certain distance from the two holes. And what you measure is essentially the visibility of the fringes here, and they are related to the first order coherence. So the first order coherence is essentially a measure of the phase coherence. And we call this also first order coherence. There are other ways to measure the coherence, and that is achieved, and this is the second order correlation function, and that is given by this correlation. So the intensity that is measured in a position of the beam on a screen, and the intensity that is measured on a different position on the screen, and is also normalized. And this gives is the base of an interferometer that is ABT interferometer. These are the initial of the Henry Brown twist interferometer. And essentially the scheme is the following. You have the source, you split the light coming from the source, and you use two detectors, and they are intensity detector typically, and you measure the correlation between the light that is detected on detector 1 and detector 2 that are, for example, placed at different distances just to make the intensity correlation. Well, this is a very interesting setup because it can be used in the classical regime, meaning that you measure just the intensity, but it can be used also in the quantum regime because you can detect the photon. So you do essentially a photon counting. And this is bringing me to the interesting point where you may ask, but what about higher order of coherence? Well, this was a question that has been addressed by Glauber, and is also bringing me to the definition of what is a quantum light. So at this point, of course, the electromagnetic field has to be quantized. So we have a quantum of energy of the electromagnetic field that today we call photon, and they can be measured as particles. And of course, if you detect particles, you can always look at the statistic of these particles. And in fact, this is what was done from after the quantization of the electromagnetic field and the quantum statistic of this particle. The work of Glauber, however, was to redefine in more precise terms the definition of a coherent source. So essentially, a coherent source or a fully coherent source should be coherent at any degree. So it should be first order, second order, or any order of coherence. And this is a very important step that is bringing us to the definition of quantum state of the light. As I said, this state, they don't have an equivalent in classical physics. And just to give some example, they are, for example, the entangled state, the squeeze state, the anti-bunching states. Before, of course, getting to this very special state of the light, we need to understand a previous step about the statistic of this light. And this was done for the first time by Arecki, and he and his co-worker, they measured the statistical distribution of a Gaussian laser source. And it was clear that these statistics became very different and was a Poissonian statistic when measuring the laser source, and it became instead a sub-Poissonian statistic when measuring the thermal light. So this was a very fundamental step that was done at that time. So essentially now we need to treat the light as particle and to measure the statistic of this light. Now let me go back to the question of the free electron laser. As I said, to make a laser in the X-rays, essentially what you would need in principle is a resonant cavity. That cannot be done. How can we, however, try to have a quantum light with a free electron laser? Well, the idea was to seed the electron bunch with a seeding laser. The field of the seeding laser has to be several order of magnitude larger than the spontaneous emission of the electron bunch. And in this case, what's happened is, although there is not a real consistent theoretical description of this interaction, but what's happened is that essentially the character of the laser light, for example, the fact that you are using a Poissonian light, has to be transferred to the electron bunch, and after the radiator, this character is transferred again to the photon bunch that is generated, and that would be, of course, an higher order respect to the seeding light, meaning that, for example, if the seeding light is at 100 nanometers, you may have out of here even 2 nanometers, right? This is something that has been already demonstrated, as I will show soon. But the question is, what about if here I am using a quantum light? That means, for example, a squeezed laser light. Would I obtain here a squeezed FEL light? This is a question that still needs to be addressed. But why are we paying so much attention to the coherence of the FEL light? Well, we know, as we said before, that in the Sarge mode you will have many spikes, and probably these spikes are incoherent one respect to the other. So the overall bunch of this light is not coherent. Instead, if you are seeding the electron bunch with a laser pulse, you will have a quite single pulse, which is, of course, very, very close to what you expect from a real laser. But of course, having a pulse that is narrow in bandwidth, that doesn't mean that is a Poissonian light. About the transversal coherence, of course, you can measure the transversal coherence in many different facilities. And as you can see here, for example, at CLS, FLASH, SACLA, and of course also at FERMI, you may have some advantages about the transversal coherence. But in this case, the advantages are not, I would say, so interesting as the advantage that instead you will have with the longitudinal coherence. Well, the longitudinal coherence was measured first in different facilities at FLASH, PAL-XFEL, and also at FERMI. But remember that the measure of the longitudinal coherence at the first order is something that is really related to what we'll call the classical coherence. So it's a phase coherence. And of course, because FERMI is producing pulses that have a very high monochromaticity in terms that is a narrow band, the coherence at the first order is extremely good with respect to the Sarzi process. But the real question is, what about the second order coherence? Well, that was a very interesting experiment. That was done on a beam line at FERMI using Embury-Brown and twist interferometer. That is a variation of the Embury-Brown twist interferometer, I will say. And of course, FERMI can be used in a Sase mode as well as in the seated mode. And well, this measurement has been done using this optical scheme, where you can measure simultaneously the dispersion of the light, the spectrum of the light, if you like, and you can measure on a CCD detector instead the light that is spread on a significantly large detector, and you can measure the correlation between different points of this detector. That was, in my opinion, a quite interesting and smart experiment. Well, what you can see is that actually when the FERMI FEL is seated, you have a very high degree of correlation, and actually what is turning out respect to the correlation that you can see when it's in the Sase mode, the correlation function is equal to 1. That means that the light that is generated here with the seated FEL is a Poissonian light. So in this respect, we can say that this light is very similar to a laser light, but this is not yet a quantum light. To be a quantum light, as I said, we need to do something else, because it has to be coherent at any degree of coherence. Nonetheless, of course, having this light, if, for example, making use of the transversal coherence, you can, for example, produce the diffraction of an object, and with the phase retrieval, you can reconstruct the image. Well, this was an experiment done by Eric Chapman in 2006, And many progresses has been done in this respect. But still, I think that the main outcome that is expected from this kind of experiment, where the final target is to have the lateral resolution that is close to the lateral resolution that you can have in the hardest rays, of course, that you can have with transmission electron microscope, is still something that is to come. Another interesting feature is that the experiment that you can obtain using the transversal coherence, if you can generate light that is circularly polarized, of course, you can distinguish, for example, as in this case, the magnetic domains. And actually, this experiment has been also looked at the pump probe technique has been looked at the dynamics of the magnetic domain. And that, of course, is a rather interesting achievement that combine the transversal coherence with a very short pulse, the tunable light, because in this case has been tuned on the copper 3p edge. And of course, in the pump probe configuration, you can look at the dynamics. But probably the more advanced experiment that has been done with FERMI was made possible because of the coherent control. And this time, we are talking about the longitudinal coherence, not the transversal coherence, where Kevin Prince and co-workers, they have been able to look at the asymmetry versus the relative phase in an experiment in gas phase, and they were able also to follow in time the shape of the orbitals in a gas. So transversal coherence and longitudinal coherence. Now, the point is, as I said, that Glauber's criterion for the full coherence requires the correlation function of any order rather than one. And this criterion is satisfied by the Glauber coherent states, where these states are essentially complex numbers. So, as I said, if we have a light that is has a degree of coherence of 1, it will have a Poissonian distribution. If I have instead a quantum light, so again, for example, a squeeze state of the light, I will obtain a light that is eventually super Poissonian. So it is narrow. And also this is detected through the photon detection. So essentially, what you can do in the experiment is to measure the correlation function, and you look at the possible deviation of the ideal distribution function that can be sub-Poissonian or super Poissonian or just a Poissonian line. And this is something that we would like to use to characterize the possible quantum light in the seeded FEL. But we have to define a strategy for this for this measurement, meaning that if I see the FEL with a squeeze state, I'm wondering if the FEL light at higher harmonic than the seeding is still in the squeeze state. And the point here is that, of course, you have to deal with a quite bright light source, and to measure, in this case, the photon statistic is not easy because you have to work with a large number of photons. And the direct photon counting, maybe counting photon by photon, may not really work. So we designed this strategy that actually has been used also for tabletop laser. What you can do, of course, is if you have the laser light that is coming, you can use a neutral filter, and you can reduce, of course, this light. But you can also consider the case of, instead of measuring the photon statistic, what you can measure is the off-click statistic. So no light is registered. The off-click probability, it depends on the photon distribution. The more photon, the less likely the detector will not click. For a percent efficiency, this is equal 1, off-click are not possible. Reducing the efficiency, we can retrieve the statistic of the off-click. And you need more neutral filters here, and to do the statistic at different intensity of the light. What we did essentially was just a simulation, and the statistic that we have simulated using the FEL, it seems to be very well fitting the theoretical distribution. And now I'm coming to the last point of my presentation here, my talk, of course, is the detector. We need a detector of very, very low noise, very high quality, needs a fast response, a small dead time, and of course, a high quantum efficiency. This detector probably already exists, and we are now on the process of testing this detector. There are also something advantages of using, for example, the CMOS sensor array. They can be operated in the Geiger mode. They have a very fast response and short dead time, operative at all voltages, direct integration on the chips. Pixel can be arranged to match the FEL spot diameter, and selective turn off of pixel for detection efficiency. So this is the working process. So what do we expect from this? Well, these are the perspective. We want to characterize the coherence of a seeded FEL in terms of quantum state. We still have to test what would be the best strategy. In the recent discussion, we end up with the idea that probably that can also be done measuring directly the photon statistic, so avoiding this complicated model that we call the non-click statistics. What are the motivation? Well, we will, of course, collect complementary information about the coherence with respect to the correlation function. And we hope to be able to discriminate non-classical feature of the FEL light. That meaning that the seeding of the FEL is not just a way to generate a narrowband pulse, but if I manipulate the seeding light in terms of, for example, of creating anti-bunching or creating a squeeze state, to see if this characteristic can be transferred to the FEL light. Of course, the simulation that we had done so far, it seems to work for a large number of photons. With large number of photons, I mean we had simulated up to 1,000 photons per pulse. Of course, they can be reached by neutral filter, and this we will also avoid the photon counting in the X-rays that as a low efficiency. Well, if that will be possible, again, we will finally have a source that is operating in the EUV and very soft X-rays with the full characteristic of a laser source. Thank you for your attention.